Hello everybody. In this video, we will run a velocity analysis for the mechanism presented in the picture. So, feel free to pause the video and read and understand the problem statement before we start our solution. Alright, so what do we have in here? We have three bodies, right? We have our disk here. We have link BC here. And we also have link CD. In the problem statement, they ask us to find omega and alpha of this little link. However, this problem is quite lengthy. That's why I decided to split it in two parts. In part one, which is your pre-class assignment, we will run velocity analysis for the entire structure. And we will end up at the end with this value and also this value. In other words, we will know every single velocity in the system. Velocity analysis must be usually run before the acceleration analysis. So just please keep it in mind. Even if we ask you to find angular acceleration, that doesn't mean that you should go right away for acceleration analysis. Usually you should run velocity analysis. You should write velocity analysis first. Okay, without further ado, let's run our velocity analysis for this mechanism. So I would actually run velocity analysis for between these three pairs of points. Between B and F, then between C and B, and then between D and C. So I can write in here, for example, velocity B is equal to velocity F plus omega of certain body times vector R B with respect to F. Of course, in a couple of seconds, I will ask you to pause the video and think omega of which body is in this expression. And also, let's maybe put these dependencies between these three pairs of points in the picture. So we are going to analyze such linkage. So we will start from B with respect to F. So it would be this vector. So this is R B with respect to F. Then we will also run such analysis and such analysis. So this is RCB, and this one is RDC. Okay. So I can also write down these three expressions in here. Velocity of point C is equal to velocity of point B plus omega of certain body times RCB. And analogically in here, velocity of point D is equal to velocity of point C plus omega of certain body times r dc. Okay, now if you would like to, feel free to pause the video and think what three different bodies, what three different subscripts I should put in here in the subscript of these omegas. Feel free to pause the video. Okay, so for those of you who got it right, congratulations. And for those of you who just are watching this video to put their notes together, here is the correct answer. So this omega is omega of disk. This omega is omega BC. And this omega is omega CD. I believe that we have only this quantity in the picture. Yes? Let us put two other quantities in the picture as well. So omega BC is omega rotating this body. So this is omega BC. And this one will be omega CD. Please observe that I assume positive direction of these two omegas. Direction. By positive, I mean, of course, counterclockwise. Okay. So let us start our velocity analysis finally with the first expression. Let us do B with respect to F of this expression. First of all, you can observe that VF is zero vector, due to no slip condition. Let me scroll up the board. Yes, you can clearly see that our point F, that the velocity at point F is zero, due to no slip condition. Then, I believe that they told us that omega of disk is 0, 0, minus 4. And now the question is, what are the components of this vector, RBF? Let me scroll up the board. RBF is here. So you can clearly see that its components at this time instant are R, and 0. Okay, let's write down our determinant. IJK 0, 0, minus 4. If I remember correctly, R was equal to 2 feet. Yeah, so I'm just gonna put in here 2, 2, and 0. Okay, let's solve the determinant. This is 8, this is minus 8, and this is 0 feet per second. Okay, we are done with our first step of our solution. We run velocity analysis between points B and F. Okay, 8 and minus 8 makes sense. Okay, now second step of our solution. Velocity analysis between these 2 points. Okay, so we can write in here VC is equal to 8 minus 8, 0, plus 0, 0, omega BC. Please keep in mind, please recall that we assumed positive direction of omega BC times this vector. Let us figure out the components of this vector, RCB. Okay, RCB is this vector, is this long vector. And they told us that L is equal to 10. This is 10. And we also know the slope of this rod. So I think that the fastest way to figure out the components of this vector is following. I think that you remember this Pythagorean triangle, yes? Triangle 3, 4, 5, yes? If we copy the triangle here, and if we multiply it by 2, let's just multiply it by 2. We will end up with some larger triangle, yes, of sides 6, 8, and 10. So these are exactly the components of our RCB vector. Our RCB vector is basically here. Oh, actually, I can do it like that. Oh, excuse me. So this is our RCB vector. So I can plug in here 8 minus 6 and 0. Okay, so this is just a small digression. I'm more than sure that most of you know that. So now let's solve this determinant. So this will be ijk of 0, 0, omega BC, 8 minus 6 and 0. And this is exactly 6 omega BC, 8 omega BC, 0. Okay, so our VC is equal to 8 plus 6 omega BC minus 8 plus 8 omega BC and 0. Okay, so our VC is equal to VCX, VCY, and 0. And VCX and VCY are respectively given in this vector. Okay, we will leave our finding in this form right now. Now let's do third part of our velocity analysis. Which is velocity analysis between points D and C. Okay, so now we can write, maybe before we write anything, please observe that VD is 0, because D is fixed, right? If I scroll up the board, you can clearly see that that point D, that is here, it is fixed. That's why velocity of D is 0. So we can write 0, 0, 0 is equal to what we just found, so this vector, plus 0, 0 omega CD. Just recall again that we assume that CD had positive direction times components of this vector, RDC. Let me scroll up the board just because I need to remind myself where that vector was. Oh, it's in here. It's this short vertical vector. Yes, and I believe that components of RDC will be 0, minus 2, 0. 0, minus 2, 0. Okay, let us solve this determinant. This will be ijk 0, 0 omega CD 0 minus 2, 0. And this is equal to 2 omega CD 0, 0. Great. So we ended up with 0, 0, 0 equal to 8 plus 6 omega BC plus 2 omega CD, and in here we have minus 8 plus 8 omega BC and 0. Great. So we ended up with two equations and 2 unknowns. Let me double check with my notes if I didn't do any mistake in here. Okay, it looks like everything is fine. So we will end up with 2 equations, as I mentioned, and 2 unknowns, because we have 0 is equal to 8 plus 6 omega BC plus 2 omega CD, and 0 is equal to minus 8 plus 8 omega BC. You can clearly see that we have 2 unknowns in here, because this is an unknown and this is unknown. Okay. From equation number 2, you can clearly see that omega BC is equal to 1 radian per second. And we obtained a positive value. That means that our omega BC vector-wise will be 1k radian per second. Or if you prefer vector notation, you can also write 0.001 radians per second. Okay, now omega CD from this expression will be equal to half times minus 8 minus 6 times 1. So this will be minus 7 radians per second. Okay, so our omega CD vector-wise will be minus 7k radians per second, or 0, 0 minus 7 radians per second. Of course, this vector will rotate clockwise, and the other one will rotate counterclockwise. Okay, so this is the end of our velocity analysis. Let me summarize everything we found. So after velocity analysis, we knew velocity of every single point in our system. In particular, we know omega BC, that is equal to 0.001 radians per second, and omega CD, that is equal to 0.0 minus 7 radians per second. This is the end of velocity analysis, and during our discussion, the synchronous discussion, we will start acceleration analysis, and we will use these findings in our acceleration analysis. The end of velocity analysis. In the next video, I will show you how to run acceleration analysis. All right, so thank you for your attention. I hope that my explanation was clear, and I hope to see you on Friday in class. Bye.